Alright, hi everyone, welcome to my YouTube channel, City of Electrons. And in this video, we are going to talk about this Field Effect Transistor small signal analysis. Okay, so for this part, the idea is this: the Field Effect Transistor. Okay, this is just an overview of Field Effect Transistor, so let's just quickly read through this. So Field Effect Transistor, that's FET. Field Effect Transistors amplifier provide an excellent voltage gain with added feature of high input impedance. That's something to take note of. They have high input impedance. Now they also consider low power consumption configuration with good frequency range and minimal size and weight. Now the Field Effect Transistor device controls an output drain current. So what this guy controls is this ID, output drain current. This is what it controls, ID. And what controls it? VGS. This is the gate source voltage, and from this you can see that FET device controls an output drain current, which is this drain current, by means of a small input gate voltage, VGS, gate to source voltage. In general, FET is a voltage controlled device, okay, because this is what is controlling output current. The gate voltage is what's controlling the output current. So it's a it's a voltage controlled device. Note that output current is the controlled variable. This is what is being controlled. This is what is taking control. This guy controls something. What does it control? This. Okay. For BJT, it's a current control device, because BJT will control the output current using the base current. So BJT is current control. FET is a voltage control. Now, while the BJT had an amplification factor of beta, the FET has a transconductance factor GM. Okay, of course, conductance is kind of this inverse, and we use transconductance because in this case we are now having current over voltage. Note that when we have from Ohm's law, this Ohm's law, Ohm's everywhere. So from Ohm's law, V equals what? IR, right? And when you have R, V over I, of course this is your resistance now. When you make R subject formula, you have V over I. But in this case now we are saying that change in gate to source voltage, which is this guy, change in gate to source voltage can be determined using the transconductance factor GM in the following manner. So change in the drain current equals the transconductance factor multiplied by change in gate to source voltage. And when you make transconductance subject formula, you have what? Change in current over change in voltage. So you have current over voltage. Meanwhile, in resistance from Ohm's law, it is voltage over current. It is voltage over what? Current. So where we have current over voltage, that is where we see it as transconductance. Okay, conductance, the like inverse, but now it's change of current to voltage, so transconductance. Okay, and of course when we say change of this to this, we are talking about differentiation here. How does the current change with respect to change in a gate to source voltage? So as we change this gate to source voltage, what happens? Okay, what do we see now? Where ID, which is this, is defined using the Shockley's equation. So what we are going to do now, we are going to differentiate ID. That is, we are differentiating the Shockley's equation with respect to what? VGS. So GM equals this. So now let's take this differentiation. quickly. So we are differentiating in the Shockley's equation. Okay, of course IDS is what we have here, and when you differentiate this, it's just like using a product rule of differentiation and the quotient rule. So using the quotient rule, when you differentiate this, of course these two will come and multiply this here, so you have two IDSS. That's what you have here. Okay, and then when we differentiate what we have inside, and the result we use it to multiply what we have outside. Clear? We differentiate this, meaning take this to multiply this, have it outside. Then we differentiate what we have inside, the result multiply outside, then the inside remains the same. Good? So let's go. So yeah, 2 multiply this, we have that. Now let's differentiate what we have inside. 1, differentiate 1 with respect to VGS. There's no VGS here. This is a constant, so it will be what? 0 minus. Now put this in brackets. We want to differentiate VGS over VP using the what? Quotient rule. Now in the quotient rule, you do what? You hold the bottom, you hold this one, differentiate the top. When you differentiate VGS with respect to VGS, you get what? 1. So 1 multiplied by this minus. This minus is from the quotient rule, which is what? U dv minus v du all over v squared. So this is the v part, this is the u part. Alright, so this minus is coming from the quotient rule. Hope that's clear. So the next thing is what? V du. So now we hold. Okay, the first part, I think I didn't write this thing correctly. It's supposed to be like this. Hold the bottom, v du minus u dv. Yes, this is how it should be. Okay, so we hold the first one, hold this one, keep it here. Hold meaning we do not differentiate it, and then we differentiate the top. We have it here. Minus, which is this minus. Now we hold the top, VGS, we leave it there, and we differentiate the bottom. You differentiate this because there's no VGS term here, it's a constant. You get what? 0. Okay, that's 0 multiplied by this. So this part is out. You just have VP. Okay, that's 0. You just have VP. Note that we just differentiated this one, Abby, which is this, and then this part will still remain, to still be there. Okay, so let's continue. So 2 IDSS, that's what we have here, correct? Now this is 0, is out. What we left is what? VP. That's what is left, VP all over VP squared. Oh, I forgot to mention this thing. We've done this. Doing this quotient rule gave us this part, minus. Doing this gave us this part, quotient rule, all over v squared. So this one, which is the v, will be what? Squared. That's why I have this. That's where we have this. So this 0 VP times 1 VP all over VP squared, all over VP squared. VGS times 0, that's out. Then this guy remains, which is what you are differentiating now. It remains inside. So we just have to open this bracket. But before doing that, let's simplify. 2 IDSS. Now, looking at this is VP. This is VP squared. Meaning we have VP under with another VP. Of course, VP squared is VP. So one of the VP under will cancel one of the VP on top. So what you have is what? 0 minus 1 over VP. And this thing remains the same here. Okay, so we'll come down. This gets here. And then this is 0, of course. Okay, it's 0, of course. So what happens now? This one we've differentiated now, minus 1 over VP, comes out to multiply this. So we now have minus 2 IDSS. 1 times this is the same thing now. VP multiply this under. So we just like we brought out this part. to multiply this. That's why I have minus 2 IDSS over what? VP. This inside remains the same. Good. Now, note that for an n-channel JFET, VP is usually negative. It's usually negative. If you look at the example we worked in the last video, VP given was what? Negative. And when you look at the graphical method, let me see if I can quickly see that. For an n-channel JFET, it is even shown in the graphical method. Yes, look at it. VP is usually what? In the negative axis. It's usually negative. So on that, based on that, therefore we take the absolute value of VP to ensure GM is what? Negative. I mean, it's positive. So absolute, when you take the absolute value, that means this guy here, this 1 over VP, taking absolute value of minus 1 over VP, absolute value meaning your minus sign goes off. Okay, so we will now have this as the expression, just the minus sign out, the parentheses remain the same, and you have absolute value. Okay, now where the gate to source voltage VGS is 0, we have GM as 0. So when GM, gate to source voltage, is 0, we have, it's called GMO. We take it as GMO. Okay, so to calculate GMO, it means here is 0. Look at it, here is 0, and if you make there 0, this part will be 0, and here will be what? 1. So everything here will just be 1. So 1 times everything here, you have GMO as just this part. Are we seeing it now? So thus we can write GM can be written as GM equals GMO, then this part. Why? Because GMO will resolve it to be this, and this is exactly this first part. Sorry, this GMO is exactly this first part. So instead of writing this, we can just write GMO in this place, and that's what we have. That's what we have here. Look at it. GMO is this, and this is same at this point. So GM equals what? GMO, and we have this part is the same. Okay. So oh boy, I gotta shut down now. So that's all for this video. Okay, so the next video we'll work an example on it, okay, using what we've learned so far. So like, share, subscribe, comment, and I'll see you in the next video. Thanks for watching, and bye for now.